Good morning, friends. I'm going to explain you the concept of oscillator along with the detailed description of RC phase shift oscillator in this session. And the concept of oscillator can be explained with the help of an amplifier. So treat this as amplifier with the gain of A in its forward path, and if we connect a feedback network with the gain beta to this amplifier, and the output of feedback network is again given as an input to the amplifier, and after satisfying a criterion named Barghasan criterion for this network, then this network becomes oscillator. I repeat, this network, if this network satisfies Barghasan criteria, then this network becomes an oscillator. Means an amplifier becomes oscillator after satisfying Barghasan criteria. And the Barghasan criteria is if the gain of the forward path multiplied by the gain of feedback path, then this product of forward path gain and feedback path gain, if it is unity, a 1, means you can also take this as absolute value. Absolute value of the product of forward path gain and the feedback path gain is equal to 1, and similarly the angle or the phase shift or phase difference or the phase angle between this forward path gain and the feedback, or between the forward path and the feedback path, if this angle or the phase shift is 0 degree or 360 degree, or there is no phase shift between the forward path and feedback path, means this network becomes oscillator, or it is capable of generating sustained oscillations. By properly choosing the components, you can control the sustained oscillation into controlled oscillation, then this amplifier becomes oscillator. Repeat, if this amplifier with forward path gain A and feedback path gain beta, and if it satisfies Barghasan criterion, the name is Barghasan criteria, and what the criteria says is, if the product of forward path gain and feedback path gain, that is product of modulus value, you can say absolute value, you can take A into B will be 1, and the angle or the phase shift between the forward path and the feedback path must be, there is no phase shift, or 0 degree or 360 degree, you can take it in either way. So if any amplifier with feedback satisfies these two conditions, then the amplifier become oscillator. With this small introduction, we'll move to the detailed description about RC phase shift oscillator. RC phase shift oscillator is one type of oscillator in which the feedback network is constructed with the help of 3 RC pairs. For forward path, for amplifier, we can use operational amplifier based amplifier circuit. Its input resistor is R1 and feedback resistor is RF. Its output is Vout, and we will also have a resistor named COM, that is compensation for biasing effects, and this network is taken as amplifier network with a gain A. So here I am circling it with dotted lines. So this network alone is called, is taken as amplifier. And the feedback path, feedback means output is connected to input. So this output is connected to input side of the operational amplifier with a feedback network, as I said already, like 3 RC pairs. Drawing one RC pair, CR, the second one C, R, and the final one C in and R. So all the resistors must be grounded, and the output of the 3 RC pairs are again connected to the input side of the amplifier. Now the total circuit of RC phase shift oscillator is ready. And this, secondly, I am also separating this with the help of a dotted line. So this network is called feedback network with a gain beta. So the network is ready. We have, for forward path, we have the amplifier, operation amplifier with gain A, and for feedback path, we have 3 RC pair network with the gain beta. Because of the RC pair, we are able to produce the gain beta, and will be able to solve these two things by using this network. If you are able to solve these two things, product of AB is 1 and angle of AB must be 0 degree or 360 degree, then this circuit will become oscillator. This amplifier circuit will become oscillator, provided it must satisfy this Bargasian criteria, both the criterions. Here we have to solve, and we have to consider each part separately. We know about this operational amplifier configuration. Since the input is connected to this negative terminal and the positive terminal is grounded via R-COM, this amplifier is an inverting amplifier. A is an inverting amplifier, and its gain A equals to minus feedback resistor by input resistor. You name this as Roman letter 1. And we don't want to analyze further because it is a well-known thing to everyone who knows the operation of operational amplifier. And the second part, we have beta, we have 3 RC pairs. By nature, all the RC pairs, a single RC pair is having 60 degree phase shift. So all the RC pairs are having 60 degree phase shift. So 3 RC pairs will be having 180 degree phase shift. And if you consider the equation 1, and in its expression you have a minus, so this is also having 180 degree phase shift. So in the feedback path you have 180 degree, and the forward path you have 180 degree. Both the phase shifts are cancelling each other, or you can take this in other way, the phase shift is 0 degree. So by nature, by considering the structure of this circuit, we will be having 0 phase shift. So the second condition of Bargasian criteria, that is angle of forward path and feedback path is 0 degree or 360 degree is satisfied. So the second condition is proved, and our work is to prove the first condition. We have to find this and we have to prove the product is unity. So by considering equation 1, Roman letter 1, we have already got A equals to minus RF by R1. and the remaining part we have to prove is to find beta and the product of A into beta is 1, or to satisfy the product A into B equal to 1, we have to consider the circuit components. And to solve this, we have to draw the feedback path separately. Before drawing it separately, we can name the inputs and outputs of this feedback path. Since the output is directly connected to the input side of the feedback path, the same notation you can use, V out, or output is the input to the feedback path. The total output of the circuit, initially it is 0, and after consideration it will be producing oscillation. So that output is feedback as an input to this feedback network, and the output of the feedback network is named as VF, feedback potential. So for this feedback network, the input is V out and the output is VF, and I'm going to now draw this feedback path separately. So we will be having feedback path like this. So draw the same circuit. First RC pair followed by second RC pair and finally the third one. All the R's are connected and it is grounded. Here the input to this feedback path is V out and the output of the feedback path is VF, and we have to consider the current flowing through this. In the first area or shared by first RC pair is I1, and similarly in the second one it is I2, and similarly in the third one it is I3. Here we have to consider one thing. The VF is taken across the drop from this final R, so we can directly take VF equals to the current in this, the third RC pair is I3 and it is taken across the drop across R. So you name this as equation 2. So VF is V equal to I into R. VF, the output potential across R, drop across R is R, and the current flowing through the third part is I3. So VF equal to I3 into R. So ultimately our aim is to find this I3. If you are able to find this I3 and with the help of R you can find this VF, and that VF from the previous diagram, that VF is given as an input to this inverting terminal, or it is the feedback output. It is fed back as an input to this inverting terminal. Then the operation amplifier along with the feedback will be able to produce output, that is sustained oscillations. So our aim is to find this I3. Then from this circuit we have to find individually the currents I1, I2 and I3. And by considering the first loop and the effect of I1, if you write the potential equation, the potential drop in this or potential in this capacitor is I1 into 1 by SC, because it is capacitor, and potential drop in this R is plus I1R will be equals to the other side potential. It is the output, I mean actual output, but it is input to this input to this feedback network. We out name this as equation 1. Sorry, this is 1 by SC, and this one is, this resistor is a common for I1 and I2. So this must be, instead of I1 into R, you have I1 minus I2 into R. So this resistor is common, which shares the current I1 and I2. So both the currents are flowing through this resistor. So we have to write this like this only. So if we expand this, I1 into 1 by SC plus I1R minus I2 into R equals to V out. So we can write it in order, and there is no I3 in this first equation. So I1 you take common, I1 into, here it is R plus 1 by SC minus I2 into R plus 0 I3. Since there is no I3, equals to V out. You name this as 2. Similarly, for the second region, second RC pair, you have I2 is the source current, and I2 is flowing through the C as well as this R and this R. So the equation is written as I2 in C will be I2 into 1 by SC plus I2 and I3 both currents, this resistor shares both the currents. So I2 minus I3 into R plus this I2 is also flowing through this R. So plus I2 minus I1 into R, and there is no separate potential, the path is closed, so the total potential around the loop will be equal to 0. Name this as 3. Here the current I2 flowing through this capacitor is I2 into 1 by SC, and I2 shared by this resistor along with I3. So I2 minus I3 into R. Similarly, this I2 is also shared by this R. So I2 minus I1 into R. So that is also written. The total potential around the loop must be equal to 0. That's why the equation is 0. So we can expand this. I2 into 1 by SC plus I2 into R minus I3 into R plus I2 into R and minus I1 into R equal to 0. And we can separate, and we can write this equation in order. Only one ion is there, so minus I1 into R and I2, here I2, so take I2 common, R plus R, 2R plus 1 by SC, and will be having one I3, so minus I3 into R will be equal to 0, equation 4. Similarly, consider the first loop, means the third loop, RC. Here from left to right it is first, and from the input to output it is third loop, and the loop current is I3. This I3 flowing through the C as well as and shared by these two resistors. So I3 into 1 by SC, I3 minus I2 into R, and plus I3R plus R alone. The R is the final resistor, act as a load to deliver this VF. So I repeat, I3 in this C is I3 into 1 by SC, and this R is common for I3 and I2, so I3 minus I2 into R, plus in this R I3 alone is flowing, so I3 into R. So the firstly you can write I3 into 1 by SC. So I3 into 1 by SC plus I3 minus I2 into R, I3 minus I2 into R, and the final one I3 into R plus I3 into R equals to the total loop around the potential. Again, the total loop around the potential is 0. And you can name this as 5. We can also expand this as we did in the previous equations. So I3 into 1 by SC plus I3 into R minus I2 into R plus I3 into R equals to 0. And here there is no I1, so 0 I1 minus only 1 I2, so I2 into R plus here I3R, here I3R, and one more I3 into 1 by SC. So take I3 outside, R plus R is 2R plus 1 by SC equals to 0. You name this equation 6. Now the finished equations are equation 2 for first loop and equation 4 for the second loop and equation 6 for the third loop. So by writing these equations separately, we'll be having the separate current equations, and from equation 2 we have I1 into R plus 1 by SC minus I2R plus 0 I3 equals to V out. And from equation 4 we having minus I1R plus I2 into 2R plus 1 by SC minus I3R equals to 0. And from 6 we'll be having 0 I1 minus I2 into R plus I3 into 2R plus 1 by SC, which is equals to 0. Now these three equations can be written in the form of matrix. So we can draw a 3 by 3 matrix for these three equations by considering all this I1, I2 and I3 along with the potentials available in the loop. So from equation 1 we have the factor of I1 is R plus 1 by SC, and for I2 it is minus R, and for I3 it is 0. Similarly for the from the second equation it is minus R, 2R plus 1 by SC and minus R. And from the equation 6 or the third current equation we have 0 for I1 and minus R for I2 and 2R plus 1 by SC for I3, and here I1, I2 and I3 are marked for all the three equations. And in the right hand side after equation we have V out, 0 and 0, the loop potentials, and this is a general matrix. And from this the del, the total value of these current values, can be calculated by considering only these matrix values r plus 1 by sc minus r and 0 minus r, 2r plus 1 by sc minus r, 0 minus r, 2r plus 1 by sc. Then del becomes r plus 1 by sc into this 2r plus 1 by sc. The previous equation appears in the form of a plus b whole squared formula. So this is 2r plus 1 by sc squared, a plus b whole squared. So we can expand it in the next step. Minus r squared plus r into minus r into 2r plus 1 by sc. Next, the del becomes r plus 1 by sc into, so this appears a plus b whole squared. So we can expand it with the help of a squared, that is 2r squared. So 4r squared plus 2ab, 2 into a into b, 1 by sc, plus b squared, 1 by s squared c squared, minus an r squared is available, plus for the second term r you can keep as it is, minus r into 2r, it is minus 2r squared, and minus r into 1 by sc is minus r by sc. Next, del becomes r plus 1 by sc into, here it is 4r squared, here will be having 4r by sc plus 1 by s squared c squared minus r squared. So 4r squared minus r squared, we can convert this as 3r squared plus 2 into 2 into r into 1. So 4r by sc plus 1 by s squared c squared, here in the second term, plus r into minus 2r squared, that is minus 2r cube, then r into minus r by sc minus r squared by s into c. Then del becomes r into, I have to multiply all these 3 terms, again 1 by sc into all these 3 terms. So r into 3r squared is 3r cube, r into 3r squared is 3r cube, plus r into 4r by sc is 4r squared by sc, plus r by s squared c squared, since r into 1 by s squared c squared, again plus 1 by sc into 3r squared is 3r squared by sc, plus 1 by sc into 4r by sc is 4r by s squared c squared, plus 1 by sc into 1 by s squared c squared is 1 by s cube c cube, here minus 2r cube minus r squared by sc. So this del equation, s cube c cube is the common and it is the bigger value for all these terms, so you have to take that as common term in the denominator, s cube c cube, and here only 3r squared, there is no denominator term, so 3r cube, sorry it is 3r cube into s cube c cube, since there is no denominator, plus here only 4r squared available, 4r squared by sc, so s squared c squared plus r, in the denominator s squared c squared is there, so common term is s cube c cube, so r into sc, plus here you will be having 3r squared, sc is available, but common term is s cube c cube, so s squared c squared, plus here 4r s squared c squared, so sc, plus already s cube c cube only 1, minus here we will be having 2r cube, so 2r cube, there is no denominator, so c cube s cube, minus r squared, denominator is sc, but common term is s cube c cube, so s squared c squared. And next, the new del equation becomes, we'll be having 3r cube s cube c cube. Here 2r cube s cube c cube s cube. So both the terms are having r cube s cube c cube. Here it is 3, here it is 2. So if you subtract 3, or 3 minus 2 means the remaining will be only r cube c cube s cube. We can write it in order: s cube, r cube, c cube. So after replacing these two terms, and similarly we'll be having 4r squared s squared c squared plus 3r squared s squared c squared. So if you consider these two, it will be 7 s squared r squared c squared. Here 1r squared c squared s squared, it is in the minus. So 7 minus 1, it is plus 6 s squared r squared c squared. So these three terms will be eliminated, and the remaining term plus 4 src, simply src. So 5 src plus 1 by denominator s cube c cube. So this is the current equation for the total currents I1, I2, I3, and it is named as del. And from we can name this as Roman letter B. From this equation, we have to find especially the individual current I3, as we have discussed in the earlier part of this derivation. So I3 is the final current from which only you will be able to get the feedback potential Vf. So directly we can solve I3, no need to solve I1, I2, because I3 is the final current. To solve I3, the same matrix can be used, but with a slight change of the third column must be the values of the potentials we have achieved. That is, you can consider the same matrix del. You have put del 3. So we have R plus 1 by SC minus R. Here in the previous matrix you'll be having 0, but now I'm going to put V out, and minus R, it is same as the previous matrix, and 2R plus 1 by SC, same value. Here the potential value is 0, and 0 minus R, 2R plus 1 by SC. So the third column, sorry, this one will not be 2R by SC, it will be 0. It will be only 0. So the third column in the matrix is replaced. Actually, it was in the first matrix. If you see the first matrix, it will be 0 minus R and 2R plus 1 by SC. But instead of this, the column has been replaced by V out, 0 and 0, the potential values. This is for finding this I3. So this I3 will be, we can find I3 with the help of this replacement, replacing the third column with the help of potential values. And after that we have to solve by using the same matrix rule which we have used to solve del. So now del 3 becomes here R plus 1 by SC enter, can leave this column and this row, have to multiply this with this term, so 0 minus 0, so the total term becomes 0. Already we will be having minus R, so this value is for this particular position is minus, So plus R into, have to leave this column and this row, and you have to consider these two. Again it will be 0 plus V out, the third factor, into, to leave this column and they leave this row, you have to consider these two matrix positions. Minus R into minus R, it is R squared, minus 0 into this thing, so this minus this, so 0. So this one is 0, the second term is also 0. From the third term we will be having value, that is V out into R squared. So del 3 from this modified matrix, by placing the potentials, we'll be able to get I3 will be V out into R squared. And this is especially for solving I3. And from this we can solve, or we can find I3, the output current of the feedback network, in producing the feedback potential Vf. So I3 equals to del 3 by del, the del 3 solved for I3 divided by the total current effect del. So substituting the values for del 3 and del, we have I3 equals to, for del 3 it is V out into R squared, we have derived, and for del we have already derived, that is S cube R cube C cube plus 6S squared R squared C squared plus 5 SRC plus 1 divided by S cube C cube. So this denominator part will be moved to the numerator. We'll be having V out R squared S cube C cube whole divided by S cube R cube C cube plus 6S squared R squared C squared plus 5 SRC plus 1. This is our I3, the final current which is responsible for producing the output of the feedback network. So now we have already derived an expression in the Roman letter 2 that Roman letter 2 is Vf equals to I3 into R. We're able to refer the previous equation. We have from Roman letter 2 we have Vf, the output of the feedback is I3 into R. So by using this, the above equation I3 becomes if you change that as Vf, then the I3 must be multiplied by this R. So you can multiply this equation with R. So this R squared become R cube S cube C cube divided by S cube R cube C cube plus 6S squared R squared C squared plus 5 SRC plus 1. Here, if you consider the Vf in the left hand side and V out in the right hand side, and if you move the V out to the left hand side, it will be moving to the denominator Vf by V out, which is equals to R cube S cube C cube whole divided by S cube R cube C cube plus 6S squared R squared C squared plus 5 SRC plus 1. So the Vf is output from the feedback network and V out is the input to the feedback network. So output of the feedback network divided by input of the feedback network. So this is the gain of feedback network, and we have already named this as beta. Beta is Vf by V out. So hereafter we can use this beta for this VF by Vout. Beta equals to R cube C cube. For S we can put j omega cube divided by, here for S it is j omega cube R cube C cube plus 6 into j omega squared R squared C squared plus 5 into j omega into RC plus 1. So we have omega squared is minus 1. J squared is minus 1. J cube is minus j. So minus j omega cube. For j cube it is minus j. For omega cube R cube C cube divided by, here also minus j omega cube R cube C cube minus 6, j squared is minus 1, so omega squared R squared C squared plus j into 5 omega RC plus 1. So and if we divide numerator and denominator with this term, we'll be having beta equals to 1 by, here it is 1 minus 6 omega squared R squared C squared divided by minus j omega cube R cube C cube plus j 5 omega RC divided by minus j omega cube R cube C cube plus 1 divided by minus j omega cube R cube C cube. Hence beta equals to 1 by 1, here 1 by minus j is plus j, but already a minus is available, so minus j 6 omega squared R squared C squared by omega cube R cube C cube. Here I have moved minus j to the numerator, s plus j, already minus is available. For the next term, j and j will be cancelled. You will be having minus 5 omega RC by omega cube R cube C cube. 1 by minus j is j plus j into plus j by omega cube R cube C cube minus j. 1 by minus j is simply j, that's why I have put j here. And again beta becomes 1 by 1 minus j into 6 into, here omega squared R squared C squared, so the square will be cancelled. One you will be having j by omega RC. That is minus j by omega RC. And for the second term, minus 5 into, so omega RC will be cancelling 1 omega RC, then remaining will be squares. So by omega squared R squared C squared plus j by omega cube R cube C cube. And beta equals to 1 by 1 minus 5 by omega squared r squared c squared minus j into 6 by omega rc plus j by omega cube r cube c cube. So here 1 by omega rc can be replaced by a value alpha for simplicity. So beta becomes 1 by 1 minus 5 alpha squared minus j into 6 alpha plus j into alpha cube, where alpha equals to 1 by omega rc. Now, to satisfy the Bargasian criteria, beta must be real. So, imaginary part in this beta equation must be equal to 0 to produce a absolute positive beta to satisfy Bargasian criteria. So, from this beta equation, we can name this as Roman letter 3. From this Roman letter 3, we have to equate the imaginary parts. So minus j6 alpha plus j alpha cube must be equated to 0. So j into j you can take outside, minus 6 alpha plus alpha cube will be equal to 0. So alpha cube equal to 6 alpha. If you cancel these things, then alpha squared equals to 6 and alpha become root 6. We name this as Roman letter 4. So substituting Roman letter 4 in Roman letter 3 and omitting the imaginary terms, beta becomes beta without imaginary terms is 1 by 1 minus 5 alpha squared, and if we put alpha equals to root 6 in this equation, then beta becomes 1 divided by 1 minus 5 into alpha square root 6 square. So 1 divided by 1 minus 5 into 6. This will be 1 divided by 1 minus 30. This will be 1 divided by minus 29. This is beta. So we have derived a beta for this RC phase shift oscillator, which is equals to beta equals to minus 1 by 29. So this has been derived by considering the beta is real. If the beta is real, means these two imaginary terms must be treated as 0. That's why we have taken these two terms and assigned to 0, and solving this thing will provide us alpha equals root 6, and again this alpha value is substituted in this beta equation without this imaginary part, and that equation will be like this. And if you put alpha equal to root 6, you'll be able to get beta equals to minus 1 by 29. From Roman letter 1, we have already solved, and we have the gain A equals to minus RF by R1. So by considering these two, that is beta and A, we'll be able to solve the other Bargasian criteria, that is modulus A into beta must be equals to 1. Here A equals to, can solve here, A equals to minus RF by R1 into beta equals to minus 1 by 29, and if you put modulus, this must be equals to 1. So these two minus cancelling each other and modulus will eliminate the minus. So RF by R1 into 1 by 29 equals to 1. So RF by R1 equals to this 1 by 29. If you move to the right hand side means it will be only 29, and RF equals to finally 29 into R1. So RF equals to 29 R1. If we choose RF equals to 29 R1, then you'll be able to get this A beta equals to 1. I'm proving it. So we found RF equals to 29 R1 from this expressions, and we have A beta absolute value must be equals to 1. Now A is the gain of inverting amplifier RF by R1, and beta is the gain we have derived from the feedback path, that is 1 by 29. Both will be having minus, and minus will be cancelled, so absolute value. So here RF and R1 we have found an expression, that is RF equals to 29 R1. If we choose RF equal to 29 R1, then 29 R1 by R1 into this 1 by 29. So R1 cancel, 29 cancel, this will be 1. So modulus of A beta equals to 1. The absolute value of the products of the forward path and feedback path gain is proved as unity by considering only the value of RF equals to 29 R1. This RF equal to 29 R1 has been proved by solving the expression for beta. So if we choose the value of RF and R1 in the design in such a way that RF equals to 29 R1, and properly choosing this RC values in order to match the phase, we'll be able to solve these two conditions, that is product of forward path gain and the feedback path gain is 1, and the angle between the forward path and feedback path is 0 degree or 360 degree by choosing these two networks. This is 180 degree phase shift, this is having 180 degree phase shift, and this is having 180 degree phase shift. So phase shift is 0 and the product, the gain product is 1. So these things are proved, then this amplifier becomes oscillator, and this oscillator is especially having 3 RC pair in its feedback. So the name of this oscillator is RC, and it functions with 0 degree phase shift. So phase shift, it is used for oscillations or producing oscillation without any input. That's why the name is RC phase shift oscillator. Thank you. And one more thing in this RC phase shift oscillator is the frequency of oscillation. We have alpha equals to 1 by omega RC. Here we found all the value for alpha is root 6. Hence root 6 equals to 1 by omega RC. We know that omega equals to 2 pi f. So after substituting omega, we'll be having root 6 equals to 1 by 2 pi f into R into C. then this F will be the frequency of oscillation. So F or F oscillation will be equals to 1 by 2 pi root 6 into RC. By using the proper values of R and C, the F oscillation can be fixed. Based on the value of F oscillation, the RC phase shift oscillator oscillates and generates the F oscillation frequency. Based on the requirement of F oscillation from the RC phase shift oscillator, we need to choose R and C. And one more thing in this RC phase shift oscillator is the frequency of oscillation. We have alpha equals to 1 by omega RC. Here we found the value for alpha is root 6. Hence root 6 equals to 1 by omega RC. We know that omega equals to 2 pi f. So after substituting omega, we'll be having root 6 equals to 1 by 2 pi f into R into C. Then this F will be the frequency of oscillation. So F or F oscillation will be equals to 1 by 2 pi root 6 into RC. By using the proper values of R and C, the F oscillation can be fixed. Based on the value of F oscillation, the RC phase shift oscillator oscillates and generates the F oscillation frequency. Based on the requirement of F oscillation from the RC phase shift oscillator, we need to choose R and C.